Hey there, Chem Squad! Today we're going to look at some complex Lewis dot diagrams. From last class, we looked at some of the basics in terms of how to draw out a nonpolar covalent bond, a polar covalent bond, and an ionic covalent bond. Today we'll look at a few more other features and some other techniques for drawing Lewis dot diagrams. So first of all, I'm going to start with carbon monoxide. This one's a pretty good one to show double bonds between atoms. So usually whenever we have a molecule, we want to, of course, predict the type of bond that exists by finding the difference in electronegativity. So just quickly, carbon's electronegativity is about, 2.5. Oxygen's is 3.5. When you take the difference, as well as the absolute value, it comes out to be 1.0, which we predict to be polar. So we know that we're going to need delta signs, and whenever possible, if we can obtain some kind of asymmetrical shape, that would be preferable. Now, with carbon, because carbon has 4 valence electrons, and normally we would put these 4 valence electrons like so, okay. Oxygen requires 2 electrons from carbon because oxygen has 6 valence electrons. So 1, 2, 3, 4, 5, and 6. Now, we mentioned that atoms don't like to have lone electrons. And right now, if we just put them side by side, you have one shared pair of electrons, but then you have 1, 2, 3, 4 electrons that are alone by themselves. So this is not preferable. Okay. Instead, we probably want to move a couple of things around. Okay. So first off, we can move these two together to make a double bond. And then this one here gets moved over to form a shared pair. So in the end, your carbon monoxide looks more like this. So between the two, you have a double bond. Okay. Oxygen has 2 shared pairs, and then carbon also have 2 shared pairs. Okay. The substance is polar, and because oxygen is more electronegative, the electrons are going towards oxygen more often than they are towards carbon. So we will put a delta negative sign next to oxygen and the delta positive sign next to carbon. And this would be your final answer. Okay. So double bonds, triple bonds, you always have to have the electrons between the two atoms. Okay, so usually I recommend that you draw these in pencil so that you can erase whenever necessary. The next one that we're going to look at are triple bonds, and I purposely chose nitrogen because nitrogen does form triple bonds between the two atoms. You can even draw it with double or even single, but what we've observed in labs and experimentation is that they do actually have triple bonds. So again, they start in family 5A, so they have 5 valence electrons. So I'll draw these ones a little different so that you can tell where the electrons are from. Okay, so if we drew it with just one bond, you can see right away that we have a lot of lone electrons. Okay, some of them could be likely grouped up into shared pairs, but that doesn't happen. Okay, what actually happens is that we take these electrons and put them into the middle between them, and then these ones on the outside go in between as well to form a triple bond. So this one here in particular, you just have to remember that it is a triple bond and not any other bond. So again, to redraw it, it would look like this. And this is how we would show triple bonds. So don't forget to put in the electron pair that was there already. So this one here is our correct Lewis dot diagram showing triple bonds. Now, there's a couple of others. We also have complex anions. Okay, so whenever you see a complex anion, we need brackets. Okay, everything has to be worked in a bracket. So that's what you're going to put at the end. We also need to pay attention to the charge. So negative ions means that you gain one electron from somewhere. Okay, usually from a different atom. Sometimes we like to think that there's a sea of electrons with electrons available for atoms to pick up. So in this case, we're just going to think of it like that. We're going to take the atom that is in least amount and use it as the central atom. This atom is also in family 4, just like carbon. So I will put 4 valence electrons around tin. There's 3 chlorines, and every chlorine has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. And I put 7 here as well. You'll notice that the chlorines, once you have the 7 electrons with the 1 electron from tin, that chlorine now has a complete octet, and they form single bonds. However, there is that one lone electron at the top here where it's just by itself. So for this one, we just add an electron from the outside somewhere. Because like I said, it most likely probably got the electron from another atom, or it's just going to pick an electron randomly from a sea of electrons that's surrounding the ion. Okay, and because it's an ion, it needs brackets. And since you've gained 1 electron, you need to put in the charge. Okay, so it has a 1 minus charge. So this is the correct electron dot diagram or Lewis dot diagram of tin chloride, -1. Okay. Now, I'm going to show you another complex ion here. And there's 2 things about it. Okay, first of all, it's a cation. So whenever you see a positive charge, it means that you've lost electrons. Okay, in this case, it's lost 1 electron. So because it's an ion, eventually we'll need brackets. But this is something new, a coordinate covalent bond. So let me show you how to start this. You're going to start with the atom in least amount in the center, which is nitrogen. Nitrogen has 1, 2, 3, 4, 5 electrons. Okay. We have 4 hydrogens. So I can put a hydrogen here, I can put a hydrogen here, and a hydrogen here. Okay. Hydrogens have 1 valence electron each. So already with the 1 hydrogen, you're able to make 3 bonds. But you have NH4 plus, not NH3. Okay. What we have right now, NH3, is called ammonia. NH4 plus is called ammonium. So the idea is we have an electron from hydrogen, from our 4th hydrogen, but we already have an electron pair here. So we have too many electrons. And that's why in this particular ion, you have to lose an electron. So the question is, who loses the electron? Will nitrogen lose the electron, or will hydrogen lose the electron? To answer that, we look at which one is more electronegative. So we explained last time that electronegativity is the ability of an atom to gain electrons. Hydrogen's electronegativity is 2.1. Nitrogen's is 3.0, I believe. So nitrogen is going to keep their electrons because it has a stronger hold on them. Hydrogen has the weaker hold. So it's likely that this one here will be taken away or removed. So in the end, okay, let's go like this. Nitrogen will keep its 2-electron pair. You'll have hydrogen, okay, all the other hydrogens with their shared pairs. Okay. And because hydrogen lost its electron, it can fit right above the shared pair of electrons. Okay. So this bond that is formed right here, this is what we call a coordinate covalent bond. Okay. What this means is one atom, okay, a single atom gives up both of its electrons to be shared. Between two different atoms, or to be shared between itself and another atom, let's say that. Between itself and another atom. Okay. So in this case, nitrogen is sharing both electrons with hydrogen. All the other hydrogens are basically sharing one of its electrons with nitrogen. But nitrogen, in this case, at the top with this one hydrogen at least, is sharing both its electrons. So that's called a coordinate covalent bond. Okay. So just to finish off this Lewis dot, because it's lost one electron, you put the brackets around to indicate an ion, and then you put a charge, okay, +1 in this case. The other thing that pretty much happens too, when you look at the difference between the two, the difference between these two values is 0.9. So you actually have polar bonds here, okay? So nitrogen gets the delta negative, while delta positive are given for all of the hydrogens, just to show that this is a polar bond. So, ... we now come to H2CO3. Now, I may have given you this in class as a challenging complex substance or compound to figure out. And it's actually not that bad when you kind of look at it bit by bit. So when you have 3 substances, you do need to look at all the different combinations in terms of their bond forming. So you can have a bond forming between C and O. Okay. Again, look at their electronegativity difference. and it gives you 1.0. So this is going to be predicted as polar. You're going to look at O and H. O and H. O is 3.5, H is 2.1. Take the absolute value of that. It's 1.4 polar. And you also have a possibility of perhaps C's and H's forming. Okay, so C's and H's, the absolute value of 2.5 minus 2.1 gives you 0.4, which is actually nonpolar. It's actually on the cusp. It's like a hundredth away from being polar. But right now, it seems like the majority of your substances is polar. So usually when you have at least one of them being polar, it trumps the nonpolar. And if you happen to have like one of them being ionic, polar and nonpolar, you'll likely see both ionic and polar, and perhaps even nonpolar bonds in the compound. It kind of depends on what the compound is and how you set it up. Okay, but we at least know that in this particular compound, we don't have any ions. Okay, at least not predicted. So we're predicting the highest bond type to be polar. So we're going to draw it as polar. Okay. So I'm going to take carbon because it's the atom in least amount. And I already know that you have 3 oxygens. Okay, so I'm going to put the oxygens here because that's likely where they're going to be. And now I'm going to think, okay, how can my carbons arrange their electrons? Okay, how can I set it up to show the bonds? So again, I'm going to use X's for, actually, you know what? I'm going to use a dot for carbon. Just make them slightly bigger. Okay, carbon has 4 valence electrons. I know that I can have an electron here with oxygen, but oxygen has 6, so I'm going to put 6 X's in. Okay, and I can make a single bond. Now note, there is a lone electron, but I'm going to worry about the lone electrons at the end instead of right now. Okay, once I start figuring out where some of these electrons can go, it makes life a little bit easier. So again, I fill up with 6 electrons. So you have another bond here, okay, by itself, and another lone electron. So now it comes to this oxygen. This oxygen can make, again, another single bond between itself and carbon, but then I would be left a lone electron with carbon itself. So instead, I'm going to move that lone electron down. Okay, so I'm going to get rid of that one there. It's going to be moved down to here. Okay, get rid of the arrow. Oops. Okay. So now I can put a double bond here. And oxygen will have 1, 2, 3, 4, 5, and 6. Okay, so you have to kind of make sure that everything is satisfied. This oxygen has an octet of 1, 2, 3, 4, 5, 6, 7, 8. Okay, 6 electrons from itself plus the 2 that it's sharing with carbon. That makes 8. These other 2 oxygens, currently the oxygens only have 7 electrons. But we're not done yet because we have 2 hydrogens. Well, that's perfect because these 2 hydrogens can go on the end like this. And they'll make single bonds between the oxygen and the hydrogen. So the oxygens are fine now because they all have 8 electrons surrounding it, and so does this oxygen. Hydrogen only needs 2 electrons to complete its shell, so they're satisfied as well. The only one that we have to check is carbon. Carbon has 2, 4, 6, 8. Okay, so 4 pairs of electrons, 8 electrons in total. Carbon only has 4 bonds, which is the maximum that carbon can have anyways. Okay, so you have to remember, if you draw Lewis dot diagrams where carbon or any other atom have more than 5 bonds, that's too many electrons to put in their outer shell. Okay, but what we have right now is almost perfect. The only thing that we're missing is to identify the polar bonds. Okay, so between oxygen and hydrogen, oxygen is more electronegative, so there's an electronegative delta sign for oxygens. Okay, and then hydrogens would have a delta positive sign, and carbon has a delta positive sign as well, because its electronegativity is less than oxygen's. So in the end, we don't need brackets because there's no ions and there's no ionic bonds. We only have shared bonds, that is, we have covalent bonds, and because they're polar, we put in the delta signs, and the shape of the molecule itself is already asymmetrical. So it fits in with everything that we want to have for a Lewis dot diagram. Well, this is a lot of stuff, okay? I'm not saying that Lewis dot diagrams are easy, okay? Some of them can be challenging. Some of them actually could have more than one form or shape, as long as it satisfies the rules in your guide. So make sure that as you're practicing, have the Lewis dot guideline book or handout handy, and be sure to keep checking on the little things, okay? Once they're all satisfied, once all those rules are satisfied, you'll generally have a good Lewis dot diagram drawn out. All right, so next class, what we'll do is that we'll practice some more of these Lewis dot diagrams. See you guys next time.